We do serial dilution so that we can do a very large dilution without having to use a large volume, right? We can use smaller volumes, and we actually use much smaller volumes than the particular day we did our experiment. But volumes matter, and the volumes are going to help us figure out how much we're diluting. But when you're diluting, you're adding a transferred amount into a diluent, right, or a set volume. So in this case, we added 1 into 4. That would be what we would typically call a 1-to-5 dilution, okay? Where we're getting rid of the fraction and we're just taking that number, that whole amount that you would end up with. But the reason why we can do that is because the top of the fraction is a 1, right? So we always have to make sure that it's 1 at the top. And we're not talking about 0.1 or anything like that, right? That it works out to 1. So I think all these problems were where you were only transferring 1 mil, so it was pretty much just like adding. So we had 5, 10, 10, and 3. Everyone understands that part? Okay. That's our dilution factor for each individual dilution. But the thing is, we're doing these in series, right? Where we're adding 1 mil to 4 mils. That's a 1-to-5 dilution, or 5 times dilution. But then when you're taking 1 mil from here and putting it into 9, that actual act is like diluting it tenfold. But you also have to take into consideration the first dilution you did from your original, you already diluted 5 times, right? So how do we figure out for each tube as we go in the series? We multiply, right, our numbers. So the first tube stays the same. There was nothing before it that we know a dilution factor for. So then we would do 5 times 10 would give us 50. You keep going down the line, right? 50 times 10 gives us 500. 500 times 3 gives us 1500. These are the important numbers that you need to know for when you're figuring out what your original concentration is. Now, when you look at these two plates, E and F, they end up having the same colony count. Well, you're like, well, they came from 2 different tubes. B is diluted 50 times and C is diluted 500 times. How can they be the same? Because the volume you take out of each tube is very important as well. And so you'll notice that for tube C, they took an entire mil out. But for tube B, they only took 1/10 of a mil. So this tube should be more concentrated, right? It should actually have more bacteria. They took an entire mil out, probably about tenfold more bacteria, probably about 4,000. Not at all within the countable range, right? So this is an important one to point out, that the volume that you plate also has to be taken into consideration, right? Because it'll affect. Because if you take a larger volume, you're going to have more cells, right? You take a smaller volume, you're going to have less cells, right? And that's why we have to know that volume as well. And so why you ended up with the same plates is because the same counts is because you actually ended up, because of the different volumes, about the same number of cells you were taking out of each one. That's in easiest to understand terms. Now, titer or concentration, the formula for that is you have to take all the factors into consideration, right? You need the colony count, which for this one is 140, because remember our countable range is between 30 and 300 that we go by, and only this plate is within that range. It has 140 colonies on it, right? CFU stands for colony forming units. So, and that's per 1 mil, you see? 1 mil was transferred. So in this case, that number is really not going to change, right? If you divide by 1, it's still going to be 140. But if it was 0.1, that would make a difference, wouldn't it? Right? By a factor of 10. Whole decimal point. And then we get it times by that dilution factor of the tube that it came from. So notice G came from D, right? So D's dilution factor is 1500. So we times by 1500, we get 1.4 times 10 to the second CFUs. Oh, that's just writing that in scientific notation, right? 140 in scientific notation. It's easier sometimes if you do that. And then writing this one in scientific notation, 1.5. So that way now you can just multiply these two numbers, and then you can just add your exponents, which still doesn't come out so great. So I don't know why you did it that way. But if you were to multiply it out, you get 2.1, right? Remember, it's right in scientific notation, times 10 to the 5th CFUs per milliliter, right, is our concentration, right? So if you took 1 milliliter out of that original sample, right, you should probably end up with 2.1 times 10 to the 5th cells per that milliliter. Now, if we know the original concentration of the sample we took, we can get an idea of how many in that entire volume you would have. So when you multiply your concentration by your volumes cancel out, right? So you're just left with CFUs, about how many cells. And we don't say cells. Anyone know why we don't say cells? Because each one of those colonies, we're assuming, may have been created from a single cell. Not always. So our numbers sometimes will err on the low side or the high side. What do you think? So if a single cell gave rise to that colony, our numbers would be accurate. What's another possibility? Not one cell, but 2 or 3. So our numbers would actually be on the low side, right? You wouldn't take into account those extra ones that were there. So that's another reason why we write CFU and not cells, right? So colony forming units. So there's about 2.1 times 10 to the 7th CFUs in that 100 mil volume that they started with in this example. So for this one, right, 10, they're all ones, right? So this is really easy. It's just adding 10, 5, 4, 10, 10, and 6. And then again, we're just multiplying, right? Tube A stays the same. There's nothing before it. But now we're going to have A times B. And again, this is just written in scientific notation. It's the same thing as writing 50, right? And then 50 times 4 gives you 200. Times by another 10. Now this is where it makes it really easy when you do exponents to keep track of your zeros, right? And that's why one of the reasons why we do exponents, because then we're just adding one exponent there, right? So we just change that number to a 3, change that one to a 4. 2 times 6 is 1.2 times 10 to the 5th. Again, notice that they shifted over for scientific notation. Otherwise it'd be 12 times 10 to the 4th. Right? And then you can write it 1.2 times 10 to the 5th. Okay. Which plate is countable? H, because it's between that range, right? Remember that range of 30 to 300. So we know that's the number that's the first bit of information we need, right? Is the colony count. What's the next bit of information we need for calculating concentration? The amount transferred from the tube to the plate, right? In this case, 0.1. So this one really matters, this volume, right? And what do? We take 150 and we divide by 0.1, right? And then we're going to multiply by what? The dilution factor of the tube, right, that was used to plate this plate. And that is tube E. So that's 2 times 10 to the 4th, right? When we do out our math, you should have gotten 3.0 times 10 to the 7th CFUs per milliliter. Anyone not with us? Okay. And then again, if you know the volume, you multiply by the volume, the units will cancel out, right? And then you're left with just how many CFUs were in that original volume you started with. Approximately, right? How many cells? So number 3, right? Same old, same old. Make sure colony count, right? Volume, dilution factor of the tube it came from. Had anyone not checked their math before? Okay. Do you guys feel pretty comfortable on this? Not so hard? Okay. These were all pretty easy examples. They were all 1 milliliters. Okay. Alright, so I'm not going to beat that one like a dead horse. We will move on to the next thing that I wanted to show you guys, which I probably closed out. I did because it was on my drive. So, this is the data that I put together from our Kirby-Bauer experiment. Right? So we used three different organisms. I did one of the set of plates that you guys looked at. You guys, amongst the class, we did the other. So we did E. coli, which is our representative gram-negative or gram-positive. It was our gram-negative. Therefore, staph was our gram-positive. And then Pseudomonas is another gram-negative that tends to be highly resistant to antibiotics. So notice that there's only 3 green bars on here, because there are only 3 discs that actually had measurable zones of inhibition. Okay? They were for streptomycin, tetracycline, and Cipro. What I have here, the black bars, represent what they have to be in order to be sensitive, right? So this one falls just short for streptomycin, right? For our Pseudomonas. But both E. coli and staph are above the black bar. So they're both sensitive, right? And this takes into account the average of all the data for all the plates. These bars that are represented here. So it was a little bit above 20. And I think this one had to be at like 15 in order to be sensitive. I started to type it in there, but I guess I lost it. Okay, so for the next one, again, Pseudomonas falls short of the sensitivity bar. Right? It is not sensitive to tetracycline. It's resistant. Both staph and E. coli are, but you can see staph definitely was very much affected, right? Very large zone of inhibition. Cipro is the only one where all of them were sensitive. Right? They're all above the sensitivity bar. Notice for chloramphenicol, no Pseudomonas bar. Right? There was no inhibition at all of the growth of that organism by this antibiotic. But both the E. coli and the staph were sensitive. They're both above the sensitive bar. For penicillin, we only have one organism that was sensitive to it, and that was the staph. All right, and what do we know about penicillin? Interferes with cell wall synthesis, specifically peptidoglycan. Who's got the thick cell wall? Gram-positive, right? Our staph. This is what we expect. Gram-negatives, for the most part, are resistant to normal penicillin. It can't get in past that outer membrane. Not that they don't have peptidoglycan, which some don't, but, you know, it can't get in the cell because of that outer membrane. Now, ampicillin, and we only tested E. coli against this. Well, that's not true. I tested Pseudomonas, but it was resistant completely. We didn't bother with the staph because the zones of the penicillin one was so big, we didn't have enough room on that plate. Otherwise, it would have done the ampicillin, but that one would have been huge too, right? Because it's very sensitive, as we saw, to penicillin. What ampicillin is a derivative of penicillin. It's been chemically modified so it actually can get into that outer membrane of the E. coli. And we're going to use this later. We're actually going to make E. coli ampicillin resistant. So I definitely wanted you guys to see that it is sensitive, right? Normal E. coli is sensitive to ampicillin, right? It's above the sensitivity line. So take-home message, right? We know that these drugs work in different ways, especially with penicillin. It really depends on what type of cells you're using and what type of penicillin, right? Whether it's been modified or not. All the ones that end in -cillin are modified penicillins, amoxicillin, ampicillin, right? So they can work against, some of them can work against gram-negatives because they've been modified. Some bacteria resistant, as we saw, right? Pseudomonas was resistant to a lot of the drugs. Just one of them was it actually sensitive to. I don't know how to get out of this. Escape. There we go. Alright, and I won't screw this up today. My recording like I did last time. I say that